In this video, we'll discuss L'Hopital's rule. Let's start with a limit problem. Evaluate the limit as x approaches negative infinity of x squared times e to the 4x power. So limit problems, direct substitution should be your first strategy. In this case, we're thinking of numbers that approach negative infinity. So let's start with negative 100. I know that's not very big or small, I guess, but let's just see what happens. So you plug in negative 100 for x, negative 100 squared, e to the 4 times negative 100. So 100 squared is 10,000. This is now negative 400. Actually belongs in the denominator, so this is a fraction. And e to the 400 power is a very large number, huge. Like if you stick it in my calculator, it's an old school one, it says overflow. It can't handle it. So even though 10,000 is a big number, e to the 400 power is a really big number. Okay, let's do negative 1,000. So we're getting closer to negative infinity. Even 1,000 is not even very close. But still, negative 1,000 squared will be 1 million. This ends up in the denominator again. So now this is even bigger. 1 million is a big number, but e to the 4,000 power, gigantic. And what if we did negative 10,000? Again, not even scratching the surface to infinity, or negative infinity, but still we end up with 100 million divided by e to the 40,000 power. That's crazy big. I mean, that's just beyond what we can even fathom almost. It's essentially infinity on the bottom. That number on the bottom is huge. So we end up having a number, even though 100 million is a big number to us, in terms of infinity, it's still really small compared to infinity. So this is really zero because you have a smaller number divided by a large, gigantic number. And just remember that anything divided by something huge, such as infinity, will give you zero. And then anything divided by something really small, like can't be zero because then it's undefined, but if it's like 0.00000 something, well, that means that the top number is bigger, so that equals infinity. So, just think about having the number 1 divided by, 1,000. Well, that's 0.001, 1,000th. But what if it was 1,000 divided by 1? Well, now that's a big number. So those are just easy ones to think about, but just remember that if you have something huge over something small, you end up with infinity. Something small over something huge, you get zero. Okay, L'Hopital's rule. This allows us to deal with limit problems that have indeterminate form. So what you can do, first of all, is take the limit. If you have a rational function, let's start there. A rational function is when you have a fraction, two functions divided by each other. You can deal with the limit, the derivatives of each function. So if you find that when you take the limit of a rational function and you're getting indeterminate form is 0 over 0 or infinity over infinity, negative infinity over positive infinity, or any combination of the infinities divided, those are considered indeterminate. Note, however, that these are not indeterminate, so you cannot use L'Hopital's rule on every situation. So just note that indeterminate is 0 over 0, infinity over infinity. And when that applies, you can take the derivative of the top and the bottom of your fraction and then apply the limit. You can actually use the second derivative if it doesn't work. If you use the first derivative and you're still getting indeterminate form, you can do the derivative again and do the limit of the second derivative. So you don't have to do that very often, but sometimes it does work. Okay, let's do an example. Limit as x approaches 0 of sine of x over x. Well, first thing, if you plug in 0 for sine, you end up with 0 on the top, 0 on the bottom, indeterminate form. So let's take the derivative of the numerator and the denominator. You end up getting the limit of the cosine of x over 1. Well, that's nice. because you end up plugging in the 0 for the cosine and you get 1 over 1. Done. This is actually a special trig limit, this guy right here. Memorize that. It shows up a lot, and it's very helpful to just know. So the sine of x over x, or x over the sine of x, limit approaching 0. And I guess if you don't remember, if you remember L'Hopital's rule, you can figure it out. It's just helpful. Okay, let's do another one. I'm going to show you this 2 ways. L'Hopital's rule is the easier way, so we'll do that one first. Again, if you plug in a 0 right away, you end up with 0 over 0 again. But if you take the derivative, now taking the derivative of the top, you have to use chain rule because the derivative of sine is cosine, leave the inside alone, and then take the derivative of the inside, which is going to just be 4. So 4 times cosine 4x. And now if you plug in your 0, you get 4 times the cosine of 0, which is just going to be 4 times 1, which equals 4. Okay, the other method, you might see this. If you're an AP student, you might run across this. This is just a way of manipulating. So what we do is we create that special trig function. Remember that special trig function, which was this, the sine of x over x as we approach 0? And this equals 1. This is the thing I just said to memorize. Well, we can create that situation by, using algebraic manipulation. So in this case, here's our original problem, which I have not changed. I just multiplied it by 1. That 4 over 4 is just multiplying that by 1. And if you multiply straight across, I get 4 sine 4x over 4x. And now more manipulation. Let me just separate for a minute, because now I have this situation, and that's actually the special trig limit right there. Even though it's 4x, as long as it's a 4x over a 4x. So now this is the limit as x approaches 0 of 4 times, this is a limit property when you have multiplication between two limits, like between two things in a limit, you can do them separately. That was in chapter 2, if you remember that. And then now here's our special limit here. So this is really going to be 4 times 1. You still get the same answer. Remember, this is a constant. This is always going to be 4, so no matter what x coordinate, limits are really just kind of like ordered pairs in a way, because it's asking like what is the y value when x equals 0 in this case, and this is a constant of a 4, and then this is a 1. Let's do another one. I'm going to do that crazy way that I just did to show you another example of how it can be manipulated. Again, you'll see this sometimes if you're an AP student, so it's good to know the method. Again, it's just manipulation. Like the idea is that we want to get, when we're finally done with this, I want it to look like this. And then I'll have other stuff because I'm going to need to multiply by ones. I'm going to need to multiply. Notice I have a sine of 2x, but I don't have a 2x. So I'm going to need to do this to get that 2x on the bottom that I want. And then I have a sine of 3x, but I don't have that. So I'm also going to need to do this. So this is what we want it to look like, and we're going to have some leftover stuff on the other side. So anyway, I'm going to get past this screen because it's not how we're going to do it. But that's ultimately what we want to happen, is we want this to be sine of 2x over 2x times 3x over sine of 3x. So we have that special trig limit to happen. So step 1, I just kind of separate. Again, if you multiply straight across, it's still equivalent to the original. And now I'm going to do what I want to happen again. I want this 2x with this sine of 2x. So right here, I'm really just multiplying by 1 in this section right here. And I'm multiplying by 1 right here as well. And I'm doing that just because I want that 3x in the numerator. So like my next step is going to be just to rearrange things. You're allowed to do that with the multiplication, you know, like 3 times 2 and 2 times 3 are both 6. It's called the commutative property. You're allowed to rearrange things with multiplication. So this step and this step are identical. They just look different because I wanted this 2x with this sine of 2x here, and I wanted this 3x with that sine of 3x here. So I just made this the one here and this the one here. Still, if you multiply straight across, you still get the same thing no matter what. And I'm allowed to do this because 2x over 2x and 3x over 3x both equal 1. So it's like I just multiplied this fraction by 1. Didn't change the value of it. Kind of crazy, huh? So now you end up with what we want. Check. This is the special trig limit. This is the special trig limit. This is my remaining piece that I said we'd have left over from manipulating. And we can cancel those x's. Left with 2/3 there. So this is now going to be 1, the limit of that, times the limit of that, times the limit of that. Final answer is going to be 2/3. Okay, that's the long way. Let's do L'Hopital's rule. Because again, if you plug in 0, top and bottom here, you're going to get indeterminate. You're going to get 0 over 0. So yeah, let's just take the derivative of both. Remember, if you have stuff inside, the derivative of sine is cosine. You leave the stuff inside alone, and then you multiply by the derivative of the stuff inside. So the top is going to be 2 cosine 2x. The bottom will be 3 cosine 3x. And now if you plug in 0, because we're dealing with cosine this time, you're going to end up with 2 times 1 and 3 times 1. Wow, so much better, really. All right, thank you.